else was there?
I know a couple meth addicts do the same thing.
He does it for educational purposes.
That's
So he'll spend like $200 on a Dyson hairdryer and cut it open and show you this is the cheap Chinese garbage they put inside of it, and then charge you $200 for a name. Interesting stuff.
12-year-old kids got to eat too.
Mm-hmm.
Hey guys.
Hey.
I'm back.
Welcome back.
Did you miss me?
Somewhat.
Absolutely.
Any of you guys attempt the trig homework yet?
Yeah.
I did.
I looked at it.
I'll
I'm going to do that after this class.
Yep, same.
All right.
I had one that I didn't know about, number 6. I really was unsure about that one.
Well, today we're going to do some more practice. So the other day, all we did was try to find, what did we do? Try to find given an angle and a side, we found a third side. We're going to practice that more, and we're going to do, given 2 sides, we can follow the angle. And that involves doing the inverse of the angle, which we haven't covered yet. So if you...
Also with the homework.
You already submitted the trig homework, then that sucks because you only have 1 attempt at it.
No, it's multiple.
It has 2.
It has 2 attempts.
Mm-hmm.
Good.
It didn't last night or when I looked at it.
So you guys are probably used to like John Spuler, Bill Tate, Steve. I think they all give you multiple attempts on homework, right? You haven't had me yet.
Yes.
I only give you 1 because I'm a jerk.
Well, Steve's homework last night, it only had 1 attempt.
See, I'm starting a trend.
When your problems are 100 questions long, usually you need 2 attempts.
Yeah.
Yeah. Okay. So
I
that's
agree.
the thing. That's the difference is that I only give you 1 attempt, but I knock it down to like the most important, I don't know, 20 questions or whatever.
Right.
But in this class, we're not going to have a whole lot of homework. There's going to be trig homework, a bunch of code homework, which let's look at that here in a second. I think that's it. Oh, no, there's motors, VFDs. There's a few of them, but they're not that long.
Also, on the homework, are we just entering in the number or are we entering like the label, like centimeters or?
Yeah, you don't need units.
Okay.
Just a number rounded to 2 decimals.
Okay.
So let's look at, hang on, let's share my screen. Can everybody hear me okay?
Yep.
Okay.
I'm hoping my laptop doesn't freeze up on me. I had the hardest time doing my homework yesterday because it froze up on me like 4 times. I hope I don't have a virus.
Maybe you've got a coronavirus.
Oh.
Digital
exclusive.
Did you hear what I did there?
Yeah,
I made a joke.
Ha, ha, ha. But I don't think I believe in corona, to be honest.
You'll believe it when you get it.
Well, it believes.
Those of us in the hospital believe it.
I think your laptop's got Chromebook 19.
It might. No, I don't really think. I believe it's more like a regular flu. I mean, probably a different strand.
It took me a few seconds, but I just got that. That was funny. That was good.
I'm just going to make this real simple for people who don't think coronavirus is serious. It is. Like, I've known people who've been hospitalized, ICU nurses who still don't have use of their hands. So it's a real deal.
Wow. Well, thanks for scaring the crap out of us, Brenna.
So sometimes you need a little bit of healthy fear.
Likely to die of something else than coronavirus. But
Death is not the biggest issue. There are still a lot of long-term issues being caused by a virus that we still don't know a lot about. So better safe than sorry.
My favorite comparison is
just in general, like you're probably more likely to die driving to the grocery store than a coronavirus.
For me, it's a Demerol overdose. Probably the most likely.
I mean, it's good to know your risks, right?
Very specific.
Can y'all see my screen here?
Yep.
Yes.
See all these things that I'm moving to Friday, October 9th.
Yep.
Why are you doing
This is
that?
all homework for you guys.
All
Oh
right.
my gosh.
What the hell?
It really
Why would
does
you-
not
why would
take
you do
that long, but
Looking stuff up.
there's very little actual homework for this class. So I'm going to make this available to you now. If you happen to have a code book at home, you can start working on it. The first day of lab, I'm going to check out a code book to all of you to take home.
What's
Please.
the code? Oh, the NEC.
Yeah, please bring it back. All this is I don't expect you guys to be experts on code when you graduate, but we need to be able to know how to find stuff. We need to be able to know how to navigate the book, right? So this is just to familiarize you with some important sections, and some of these sections we're going to talk about in this class, especially conduit bending. There's a lot of conduit code that as electricians we need to know about. So let me make this available to you guys. You can start taking a look at it. But you have all semester long to do it. I would not wait till the last week to start it because this is going to take you some time. But some of those, like article whatever, let's say article 240, might have 3 questions, but you still have to look through the section and find the answers. So,
So I know this is like 7 weeks away, but is our final just gonna be like some big troubleshooting ordeal or?
no, it's going to be written.
Oh, really?
Your troubleshooting hands-on stuff is just going to be a shit ton of practice.
Okay.
And, when we get to that portion, we got to get through the conduit bending stuff first. And when we get to troubleshooting, you're going to have different trainers that we can do faults on.
Okay.
And you'll see that I'm just going to start opening up. Remember how I do that? I know. Don't worry about it right now, but you're going to have plenty of stuff to do during lab time.
Cool.
What I'm thinking right now is, how many people do we have in this class?
I don't know. 15, I thought you said 14, 1 or 2.
I guess I should take attendance. Should I though? Should I take attendance?
I think we're all here.
It doesn't seem like you to take attendance.
2, 3, 4, 5, 6, 7, 8, 9. Oh, there's only 10 of us. Even that being said, what I'm thinking is when we get rolling into the labs, I'm thinking what we'll do is do like Mondays will be a big long lecture day, and then Wednesdays half of you come in. Fridays the other half of you come in, maybe. Yeah, because then if I'm giving you code books, you can spend that time, your off days, doing code homework. Yeah, okay, that makes sense. But we'll see how it all falls into place. I want to get through the conduit bending stuff, and then you'll have, first day you come into labs, you'll have conduit bending labs you can work on. You'll have code homework you can work on. Anyway,
Are we meeting this Friday?
no. Our first come into lab day will either be Monday or Wednesday, probably Wednesday. So what I'm planning on doing today is hammering home the Trig stuff. That homework is due Friday. We'll start into conduit bending PowerPoint that I'm going to use to give you guys some, I don't know if we got homework in that or not. No, but you will have a quiz over the conduit bending lecture stuff using a PowerPoint that I'm going to give you. Monday we'll take a trig quiz, so a quiz over the triangle stuff, and then probably Wednesday will be your first come into lab day. So remind me that next Wednesday when you guys come in for the first lab, there's that release form I have to have you all sign, and there's, oh, I need to check out code books to you all. And then those of you that had me for 150, please bring your, this summer, please bring your trainer in with you.
Okay.
10-4?
Roger.
All right. I'm gonna move this over here. and go over some examples of trig. Where's my paint? All right, y'all. You want to know why I had to restart my computer?
Mm-hmm.
Call of Duty buffering issues.
You're so excited. The school gave me this little drawing tablet. So a lot of you have been in class with me before, and you know when I start drawing on Microsoft Paint, it becomes pretty ugly, right?
Yeah.
This is an attempt to get me more neat. So check this out. Hello. Look at that.
Nice.
Huh?
Beautiful.
Huh?
I don't think it can fix your handwriting.
Well, I'm not saying I
Is
have
there
the
a
best
difference?
handwriting, but like when I draw a triangle, okay, so let's compare. Uh-oh, what'd you do?
Can't you just select the triangle picture?
Shh, stop.
Oh,
Everybody's
sorry.
gonna think I'm stupid. Stop.
Or you can just use straight lines
Yours
too if
is
you want.
perfect.
Oh, I know, but that takes too much time, and this is with a mouse, so I guess the mouse actually looks better.
Like,
Oh,
this is
wow,
Just
before
because
that-
I've had practice with the.
Interesting four-sided triangle.
All right.
No,
Is
you
this
should've
is
been
this
like,
gonna be
before
Let's Make Fun of Zach Day?
No,
Is that what this is gonna be? All right.
The importance of hand-eye coordination.
Okay, so
The
first,
first four-sided triangle.
this is so cool. I'm like so excited about this. I know you're all jealous. All right. Let's just make a triangle here. Why is it still writing? Stop writing. I'm not pressing it.
very jealous.
Okay. All right. Okay, so on your homework, you had something that said like if this is alpha, the angle, and then this was x, and this is y, and then it says something like alpha equals what does that look like? About, let's say it's 41 degrees, and let's say x equals let me give me a number.
3.
3 what? Miles. We want to figure out how many miles y is. So how do we start? Let's put this into steps. Step 1.
Do the
Google.com.
cosine.
Just kidding.
Use cosine.
You the cause.
Let's take a look at what are we given. That'll be step 1.
Given x, which is the
Adjacent.
adjacent angle to 41 degrees, and then you're given y,
Right.
which is the hypotenuse.
So think of it this way. For step 1, always figure out what are you given relative to the angle. So here we're given the angle, and we're given one side, which is X,
Adjacent.
and that is adjacent. How do we know it's not the hypotenuse?
Why is the hypotenuse?
Is
It's always the longest side.
the side, yeah.
Why is the
Across from
hypotenuse?
angle.
Why is y not adjacent? Adjacent means next to, right? It is next to the angle,
Correct. But
But
still,
it's directly across from the right angle.
Right.
Makes the hypotenuse.
right? Across from the right angle is always the hypotenuse. So relative to the angle, we're given adjacent. So we're given the angle and we're given adjacent. The other, what we need to find is the hypotenuse. So what's step 2? What's our trig function?
Cosine.
Yep.
Find trig function. Find the trig func.
Find the trig.
So we're given the angle relative. We have adjacent. We need to find the hypotenuse. So adjacent hypotenuse. We're going to use cosine. 3 is set up the formula. Set up the formula.
Cos 41 equals 3 over y.
Right. So no matter what, whether we're finding an angle or a side, the formula is always going to be the same. It's either going to be the trig function of the angle. So I'll put TF of the angle equals, and then something or something. So in this case, it's cosine of the angle equals adjacent over hypotenuse. And then we're just punching stuff in. Cosine of 41 equals 3 over h,
You mean y?
or y, yeah.
Okay.
So solve that algebraically. I'm going to skip steps and just swap these two. If you need me to show you that algebraically, I can. But what you end up with is y equals 3 over cosine of 41. So whoops, backspace. Backspace, stop. I don't want square root.
I got 3.98.
3 point to which what?
3.98.
3.98. Okay. Did everybody get that?
Yep.
So y is 3.98 miles. And on your homework and on a quiz, on the final, you just have to put 3.98. And I think it's rounded 2 decimals. So you don't have to put miles. But so that's what you would do given an angle and a side. What if we were to find the angle given 2 sides? A little bit different, right? We'll use the same triangle. Steps are the same. So let's say in this case, we're given that y, oh crap. We're given y equals 42 inches, x equals 34.5 inches. We need to find the angle. What is step 1? Relative to the angle, what are we given?
Adjacent and hypotenuse.
So that means we're going to use what trig function?
Inverse cosine.
Cosine.
So when I was doing those problems, when you put like cosine, like in your calculator, when you put like cosine x equals, and then you put in your adjacent over hypotenuse, wouldn't that give you the answer?
I'm not sure I understand the question, but I'll show you. Do you have one of these calculators?
I got an app on my phone that I use.
Uh-oh. Well, I'll show you what to do with this calculator, and I'll show you what this computer's app looks like. But let's run through the problem first. When we get there, I'll show you.
Okay.
All right, so we've done step 2. So set up your formula. What's the formula?
The cosine of alpha is equal to 34.5 over 42.
Yep. So just to back up a step, if you write this down first, we won't get confused. So cosine of the angle equals adjacent over hypotenuse. So cosine of, we're calling it alpha, equals x, which is 34.5, divided by 42. So we can either solve this, we can take it step by step and solve for this. So let's do that. What's 34.5 divided by 42?
.82.
So cosine of the angle equals 0.82. Now we need to solve for alpha. So if you divide cosine over here and divide cosine over here, isn't that the same as multiplying times 1 over cosine
Mm-hmm.
algebraically? Yes, it is. So forget dividing by cosine and pretend that we're multiplying both sides by 1 over cosine. So what is 1 over cosine the same as saying what?
Cosine to the power of -1.
Yeah, so it's the inverse cosine. If you take 1 over anything, you're inversing anything, right? So just so you know, 1 over cosine is the same as saying cosine to the -1st power. And this is what you're going to use on your calculator, whether it's sine, cosine, or tangent. So if you do this algebraically, that cancels, and what you're left with is the angle alpha equals 0.82 times inverse cosine, or inverse cosine of 0.82.
So are we only using the inverse when finding the angle?
When you're solving for the angle, yep.
Okay.
But you don't even need to remember that if you know the rules algebraically, right? If you take it step by step, do it slow, cosine of the angle equals adjacent over hypotenuse, then start solving, you know, algebraically. My mind works algebraically, so that's the easiest way for me to think of it. But however you're comfortable, if you need to just remember, hey, I'm only doing inverse when we're solving for the angle, you know, whatever floats your boat. So on here, I'm not sure I know how to do this on here.
Is it 34.77?
Yeah, that's what I'm getting.
Yeah, see
How
what
do I,
see with my calculator, well, the app I got on my phone, all I do is take cosine x equals 34.5 over 42 and it just give me that answer. Kind of like this calculator.
Wait, so what's the answer? I got 34.92.
Yeah, that's
That's
if
what I
you're
got.
rounding the fraction. So if you're using 0.82, you would get 34.9. But if
Okay.
you're actually using the actual fraction where you put it in parentheses in your calculator, 34.5 divided by 42, you would get the 0.77.
So which one is the right way to do it?
I guess the question is, how would Zach like us to do it?
Yes,
There it
yeah.
is.
Hey.
Lit.
However you want to do it. So let's do it both ways and see what we come up with. Except I can't. What are the numbers? Why can't I get frickin' second? Whoa, there we go. No. No. Yes. No. Okay, here we go. So, where's my mouse? There it is. So if we go, what is it? Oh, inverse cosine. Okay, I understand that. I want to go back. Okay, inverse cosine of, and then you can do the long way, parentheses, 34.5 divided by
42.
42. So 35 divided by 42, and then you hit inverse cosine, 34.77. So that's going to be the most accurate way to do it.
But you'll accept either way, or?
However you come out, if you round to 2 decimals, you should be fine. And there's a tolerance in Blackboard. And if you say, hey, I got this right, and I'll know if you got it right. But you should be fine as long as you round to 2 decimals. But I'm just out of curiosity, I want to see the other way. So what is it, 0.82 inverse cosine? 34.92. Oh, I see what you're saying. What is 34.77 and 34.92? What is 34.5? 0.82. Man, I'm surprised it makes that much of a difference. But I guess what I'm trying to say is if you put 34.9 in on the homework and it marks you wrong, just tell me. I mean, I'm going to know that you did it right. You can't guess. You can't guess what the angle is. You have to be really lucky, I guess. Anyway, you see what I'm saying, though? Understand?
Okay, but you would prefer the long way if possible.
I would prefer whatever way you are most comfortable with.
Okay.
Either answer to me is correct.
Okay.
All right. Let's do one like this. Say this is 16 degrees. Let's say this is say this is 9 inches, and we want to find this. Call this x. Step 1. What are we given?
You're given the angle and you're given the opposite.
You're given opposite.
Oh, and well, yeah, you're given the opposite and you're given the adjacent.
Cool. What's step 2? What trig function are we using?
Tangent.
Step 3, what's our formula?
Tangent of 16 is equal to 9 over x.
Who's got it?
31.39.
1.39.
31.39.
Everybody concur?
Yes.
Cool. Okay, let's say say this is 86.2 degrees. And we know that this is 1.8 meters. We want to find this. We'll just call it Y. You know why? Because why not?
Uh-huh.
What do you want to do?
What are we gonna do? What are we giving?
Would
Cosine.
it be cosine?
Yep, it's cosine.
Because we have the angle and the hypotenuse.
Yeah.
Yep, so what are we given? Relative to the angle, we've got
Opposite and hypotenuse.
You want sine?
opposite and hypotenuse. Cosine would be adjacent over hypotenuse. This is not adjacent, is it? No, it's opposite.
It's sine.
So which trig function are we using?
Sine.
Sine. And what's our formula?
Be sine of 86.2 degrees is equal to y over 8 or 1.8.
Which means that y equals 1.8 times the sine 86.2, which gives us
Which gives you 1.7 or 1.8. Wait, that's not right.
Yeah, if you're rounding, that's right. Because if you're
Yeah.
not rounding, it's 1.796.
Yep. Mm-hmm.
meters. Why is it so close to this one?
Because of the y. It's because of the angle. So y.
Because that's a really big angle, which means if this is 86.2, that means this is 3.8 degrees, right?
Right.
So it actually probably looks more like this. So this one is just barely bigger than this one.
Triangle sharp.
All right, is everybody comfortable enough with the trig that we can?
I don't know why that was signed though. Why is that? What do you mean that's opposite?
Let me redraw this triangle.
Oh, never mind. I see now.
You always have to look at when you're picking your function. You always have to look at relative to the angle that you're either given or trying to find. What else are you given or trying to find? So according to this angle, we want to find this, and we're given this. So relative to the angle, we have an opposite and we have a hypotenuse. So opposite and hypotenuse, that means we're going with sine. 10-4?
I think so. I don't know. I'll figure it out.
Let's do one more example where we find the angle. So, damn it. What do we want to name this angle?
Steve.
Steve. We want to find angle Steve. And let's say we're given this is 42 light years. And this is 41.43897 light years. Don't you just love me right now? No? Okay. What's step one?
Find what function it is, I guess.
Relative to angle Steve, what are we given?
Given opposite.
Opposite and
Adjacent.
adjacent. Step two, what trig function are we using?
Tangent.
Tangent. What the? Step three, what's our formula?
Tangent of angle Steve.
Tangent of Steve equals
42 light years over 41
light
point
years.
all that junk.
42 all over that mess.
Yep.
So if you solve for S, what are you left with?
45.39.
That sounds right, but to write out the formula, what is it? What is it?
Oh, go ahead.
The inverse tangent of 42 over 41.43897.
And does everybody know how to do that with the calculator? Do you want me to show you, anybody? Or are you happy, confident?
Would that be with our calculators that we were supposed to have for this class? That
You want me to show you?
sure.
So in this case,
What was the answer?
1.21 gigawatts.
Mm,
Actually, I didn't punch it in there, but let's find it. If you're using this calculator, you see where's inverse tangent on here?
Second function, tan.
Right, so it's in yellow above the tangent button. So second tangent will give you the inverse tangent of whatever's on the screen. So first thing we want to do is put in 42 divided by 41.3897. Whoops. Equals, and then hit second tangent, 45.42 degrees. Follow?
Wait, can you repeat that one more time? Sorry.
Yep. So in this calculator, when you hit tangent or cosine or sine or second sine, second cosine, when you do that, it's going to take the function of whatever's on the screen at that time. So the first thing you need to do is find out what 42 divided by 41.43897 equals, and then we're going to hit second tangent. 45.39. Is that different than the first time?
I think so.
I think you got the denominator
Yeah,
wrong
I
the
left
first time
it.
you put it through.
I left out the 3, didn't I? Oh, anyway, this is the right answer.
Decent.
That is decent, isn't it?
Yeah, you know I got them on both calculators.
Damn.
I'm telling you. Oh, it's hard out here, man.
Wait,
right.
so what's the right answer? That one?
45.39.
Oh. Huh.
Okie dokie.
Got it.
All right, let's take a little 10-minute break and we'll get into a PowerPoint about conduit bending.
Oh, yeah.
Before, I'll play some Jeopardy music while we're waiting. Can you hear that? Hey, sorry, we were taking a break. I just wanted to see what you guys were doing.
We're about to take a break too. We got one question left. You
Which-
can answer this question and press all of us.
Me?
Which of the following statements is false?
Uh-huh.
You said
Resistance of an open circuit practically zero. Resistance of a short circuit is practically zero. Resistance of an open circuit is infinitely high. There is no current in open circuit. Which of the following statements is false? Resistance of a short circuit is practically zero. That's false. Resistance of an open circuit is practically zero.
false. I hate this negative logic,
Yeah.
which is not
I have to ignore the question. The resistance of an open circuit is practically zero. No, that's practically infinite, so that's false. Resistance of a short circuit is practically zero. That's true. Resistance of an open circuit is infinitely high.
also true. Where did you get
Yeah,
that?
that's true.
There's no
YouTube,
current in open circuit.
that's
Well,
that's
hey,
true.
That should be true, right?
Yeah.
But a few questions ago, it said it is possible to have current in open circuit if there's enough voltage, right?
I guess if it's inductive. What?
Yep. And if there's enough voltage across
Oh.
it, like some weight, we
What a
we jack it.
crappy question. Let's
That's
tear that out.
that's really the worst one.
All right.
So we're getting ready to take a break too, man.
Cool. Hey, sorry to bother you guys. I won't keep doing this. I just miss
Not
you.
a bother at all. Not doing this morning. What are you doing? Are you walking?
No, we're taking a break
Why is your camera moving like that?
because I'm on my phone. See, I'm still on my class,
Oh.
and I'm pissing everybody off by playing Jeopardy music really loud.
You're able to piss off 2 classes this way. Actually 3.
Yeah.
So well done. You got some skills, buddy.
Mm-hmm.
You got some skills.
You
We're
guys
getting
have
ready to get into the resistance chapter,
sweet.
which I absolutely hate. You
Oh,
want to do this one? Why don't you do the resistance? What are you doing? You're doing 150? I'll do the 150 class.
I'm in troubleshooting. You want to come over here and teach conduit bending?
No, I'm going to stay here.
Okay.
I don't know anything about that.
All right.
I just hate the resistor chapter.
Yeah. Good luck.
Thank you.
Hey, good to see you guys. Have a good day.
Very, Sam.
Everybody here?
No.
Welcome back. How'd you like the music?
Great.
Good touch.
Yeah, okay. Well, folks, I'm going to put a PDF on the shared drive for you all to look at your leisure. Actually, no, I'm not. Because if I give it to you, then you can use it on the quiz. You almost had me there. Almost. But there will be parts of this PowerPoint that I will give you to use on the quiz. But I'm going to run through this with you. I guess I need to share my screen. Where are you at? Oh, this is the wrong class. I'm going to go through this sort of quickly. Any of you ever bent pipe before?
Mm-hmm.
No.
Yes. No? No? Okay. Well, we got to get wires from place to place, right? Especially since this program is focused on industrial applications. A lot of you people, when you get a job out of here, maybe, I mean, you could pick a job that, whatever. You might be doing some conduit bending, and the conduit bending is really an art. There's a lot of math involved that I always enjoyed bending conduit. It's a challenge, and I like making things that are pretty, like this picture here. Look at all that. Everything's nice and spaced out evenly. Let me, how do I, whoa, that's cool. All right. Conduit bending 101. So you see these conduits, and there's a lot of conduit supports in here that I see that we're going to talk about. But looking at this and knowing that these people did not just buy like 90-degree fittings, they actually bent all this conduit and made it look all nice and pretty like that. And you see back here on this back wall how everything's nice and spaced out. And I'm sure all of their, these are called strut straps holding these pipes to that unistrut behind it. I'm sure all the bolts are facing the same way. It's workmanship, right? It's neat and workmanlike. And you might, in your code homework, see a code section that says, shall be done in a neat and workmanlike manner. You heard that before? Basically, when it comes to anything electrical, you want it to be neat. Not just for the sake of having pride in your work, but have any of you opened up a junction box or a panel and just seen a bird's nest of cobbled up wire everywhere?
God,
It's
yeah.
not fun to work
terrible.
in, right? So whether it's you that's going to be in a panel or running pipe in the same run in the future, or somebody else, have the decency to make it look right, make it look neat. Here's another example of good pipe runs. Pretty, isn't it? The thing is, a lot of this stuff, you see how these pipes are behind the studs? And there's probably going to be a drop ceiling up here. A lot of this stuff isn't even going to be seen, but they still took pride in their work and made it look nice. This is a bad example. And I'm not sure there could have been much else done to avoid something like this, because they had to add this conduit in the back of this tub or panel, whatever it is. But I couldn't really find many examples online of bad conduit runs to show you guys.
I'll send you some of mine.
What?
Send you some pictures of mine.
Pictures of yours?
Yeah.
I can barely hear you. Is that me? That's probably me.
Why are you yelling at me?
Because I turned my speakers down.
Oh, okay.
All right, here's what's in there. Safety tools. Safety. Okay, this is lab stuff, but always de-energize your stuff before you're working on it. Safety glasses and closed-toed shoes required. Oh, this is important. And this is a Zach thing. Please don't ever, whether you're with me or on the job somewhere else, do something that you're not comfortable with, because it's not worth it. I've done things on the job that was not comfortable with, and I regret it. And I'm here to tell you about it, but it's just not worth it. And if you're ever on the job and somebody's telling you to, I don't know, do something that's you're not comfortable with or don't have training on, say no. And if they have a problem with it, then call me and I'll talk to them about it.
Hell yeah.
Here I am acting like a tough guy. But seriously, it's not,
Like, I'm about to call Zach right now.
I'm calling Zach.
I got Marty Clinch's number if you want somebody to give him hell.
Yeah, call Marty.
Line.
All right. That's no joke though. I de-energize everything. While we're on the subject, I de-energize everything I'm working on, whether it's 120 volts or not. Like it's not worth it to me. And some people, I've heard people brag like, I've been hit by 277. I've been hit by 480. It's like, why are you bragging about that? I don't care to get hit by anything. I don't like it when I'm working on my truck and like my sweaty elbow touches and I get a little 12 volt tickle, like I just not worth it to me. So it doesn't take a whole lot to stop your heart if the current path is in the wrong place. So anyway, that's my safety spiel. Here's some good examples of safety practices. If you don't have your safety glasses, you can improvise. And if I see you doing this in the lab, you get extra credit. But it depends on if you're pitching or catching. This is good. This is one of my favorites. And there actually is a guy standing up here. This is great.
Oh, shit.
Tools. When you come into the lab, you're going to need your safety glasses. I should probably add masks on here. You're going to need a calculator. I don't care if you use your phone to calculate stuff for your pipe bends. Tape measure. Pencil. Please don't. Well, we'll see about using a Sharpie. Torpedo level. Torpedo level, is that on your tool list?
I think so.
Okay. If you have one, great, bring it. If not, you can use one of mine.
I don't think so because I don't know what that is.
Oh, well, let me show you. It's a really small level. Go to my handy dandy answer for everything.
Okay.
Should we get one with the little conduit screw at the end to clamp it on?
That's an awesome question. If you want to be a good pipe bender, yes. If not, you won't use that in my labs. I will show you how to use that when we go over the Chicago bender. That little screw on the end of it's called a no dog. And I'll explain when we do the Chicago bend. Yeah, one of those.
If we just have a regular level, should we bring that instead? Or...
If you don't have a small one of these, I would prefer if you bring a 4-foot or a 6-foot level. Totally kidding. Totally kidding.
I have a 10-foot. Is that okay?
Yeah. No, you really just a small one. I will show you how to measure for bends using like a 4-foot level, but I have 2 here that you can use. So don't worry about bringing in anything. Okay. I mean, if you got a small torpedo level or if you want to bring a 2-foot level in, that's fine. But this is what a torpedo level looks like. The other one, which actually will show up later in the PowerPoint, is called a reamer. Sandra Reamer. I don't know. Whoa, look at Frank Reamer. Look at this guy. That's incredible. Okay.
Pipe reamer.
Conduit. One of these. I have one of these for this. This picture I think is in the
Looks like a
PowerPoint.
vape.
But you see these little teeth right here, these little hooks. So when you cut a pipe, like EMT, a steel pipe, you're going to have sharp burrs there, right? And when you go to pull wire in there, that's bad juju. So you want to ream the pipe. That's what this is for. I have one of these here for you to use. And this is like 1/2 inch pipe, 3/4 inch pipe, 1 inch pipe. So that's what a reamer is. Good question. All right. Different type of conduit types. Rigid, non-metallic. Here, I'll go through. I think there's pictures here. So these are 6 different types that we'll discuss in this PowerPoint. There are plenty more out there, but they're all just different raceways for different applications of pulling conductors into different, stuff. PVC, rigid non-metallic conduit. So if you see RNMC in your code book, that's rigid non-metallic PVC. Anybody know what PVC stands for?
Polyvinyl chloride.
Polyvinyl chloride. Very good. Let's see. You will see PVC run, I don't know. In industrial, you shouldn't see it run like exposed. For the most part, PVC is used underground. But residential applications, people use PVC all the time. But
I use the white one for electrical.
Do you? Good. And you still have a job?
You darn right. They pay me more for that.
White is the wrong color. White's plumbing. Nick's being funny. Come on, Nick.
You know that thing you're uncomfortable with? I don't have that. I just do whatever.
All right. Important thing to know about PVC is that they do have threaded adapters, but for the most part, it gets glued together with PVC glue. Rigid metallic conduit, RMC or RSC. These have threaded fittings that go onto the end of them. I do have a pipe threader here, but I'm not going to show you how to do it. It's an old ancient dinosaur of a threader anyway, and you have to have oil. But once you've done it, you've done it, and you know how to do it. I can put a video on Blackboard or the shared drive if you want to see how to thread conduit, but you've done it once, you've done it a million times. So RMC is rigid, got a thick steel wall, and you can kind of tell on the outside of these, they're usually galvanized, actually type 4 GRC, galvanized rigid conduit. I've never seen rigid run without that galvanized coating on it, so I don't know why they have it in 2 different categories. So if you go to the supply house like Gray Bar or Springfield Electric and ask for some rigid, it's going to have that galvanized coating on there. Everybody know what galvanizing is? It's basically like a paint almost, but it's
The nickel?
Yeah, I'm not sure what it's made out of, but it's to stop corrosion. IMC is the same kind of thing. It's just a little less, did I say sturdy? But it's made out of aluminum. It's lightweight. I stands for intermediate, so intermediate metal conduit. Same threaded fittings and threaded ends. EMT is what you guys are going to be using in the lab. Electrical metal tubing. It's probably the most common type of conduit run in application in industrial settings, at least for branch circuitry. So you'll see a lot of rigid bringing service entrance and feeder conductors in, and then EMT run to different outlets and switches and panels and stuff. So EMT is thin wall. That means that it's not threaded. It uses 2 different type of fittings. This is a compression fitting for EMT. This is a 1/2-inch coupling. So if you take 2 pipes to join them together, and what these have inside of them is actually, I'm going to pull up. I'm going to talk about flex, and then I'll show you these guys on a better camera. But compression fittings or set screw type fittings. And I'll show you, yes, I do have one of each. I'll show you both of those. So EMT is what your 1/2-inch and 3/4 what we're going to be bending in the lab. And then this is flex. It's called flexible. Guess why? Because it's flexible.
Wow.
Okay. Yeah. Flex. And then there's another kind called seal tight. It's PVC coated flex. Sometimes it has this inside of it, and sometimes it's just PVC flexible conduit. 360-degree rule. Did we talk about this? I think we talked about this the other day.
Yes.
NEC 344.26, number of bends in one run. There shall not be more than the equivalent of 4 quarter bends or 90-degree bends, 360 total, between pull points. So it's recommended that you never exceed 270, but you're allowed 360.
Can you add a pull point? Like an LB or something like that, and then
Yep.
start over? Okay.
Yep. As long as you don't have more than 360 between any 2 pulling points.
Okay. Yeah, I was.
Conduit supports. I have pictures of all these, but I'm actually going to try to show them to you. This. Unistrut. This is Unistrut. You will see this a lot, and I love this stuff. I build crap all the time with this stuff because it's sturdy and it's easy to work with. But this is Unistrut. It's they make this, and this is just steel with a little bit of galvanized coating. They make stainless steel Unistrut. They make shallow strut, so it's like half the width. But it's just a way to support something. So plumbers use this stuff. I mean, everybody uses this stuff, but you can use this for multiple conduit supports. I think in one of those pictures at the beginning of the slideshow, there was plenty of Unistrut. So I can go back and show you that if you want. Strut straps are actually these are strut straps, and you will use strut straps in the lab. But how these work are, see, these got these little teeth that grab onto the inside channel of this strut, so they can go in and twist. I'll show you. Blow my video up so I can see what I'm actually showing you guys. 10 video. All right. So this is a 1/2-inch strut strap, and you can see that if I were to put that in there, line them up, and then bolt this together, it's your bolt, turn it to the side, and you can see how that actually clamps onto the conduit in here, and then when you tighten it up, it just cinches down up against the strut and holds it really tight. This is a strut strap. This is, if you go to like Menards, they'll call these conduit hangers, but the jargon for it is called a mini. This is a mini. Same kind of thing. This is 1.5 inches conduit, and a bolt goes through there. Pretty self-explanatory. Grabs onto the pipe. What's next? Spring nuts. There's actually a spring nut in here behind this black washer, but this is a spring nut. So if I wanted to bolt something to this, like a mini, You can see why it's called a spring nut, because it's a nut and there's a spring. How these work is these little guys here grab onto the inside channel of the strut. So the spring is handy because it holds it into place while you bolt something to it. So you push in on the spring, twist it 90 degrees, and it goes click and grabs on, sitting there waiting for you to bolt something to it. They make these without the springs, but I don't know why anybody would ever use those, because the springs make it easier to work with. Beam clamps. Anybody knows what these are used for?
Rounding.
To clamp onto beams. See what I did there?
Yep.
Self-explanatory. You use this part to thread it, or it'll grab onto a beam or a purling, and then you can hang things from it. There's usually two threaded ends. These come in different size, but this one takes 1/4-20 bolts. So if I had one of these minis and I wanted to hang something from a beam or a purling, I would clamp this onto it, 1/4-20 bolt this mini to it, and off I go. That's a beam clamp. 1-hole and 2-hole straps. Can anybody guess which is which? This is a 2-hole straps. 2-hole strap. If you count the holes on this thing, there's 2 of them. 1, 2. Also self-explanatory. This is for inch and, it doesn't say, 1.5 inch. 1.5 rigid, it says. So 1.5 rigid pipe, if you were running it straight up a wall, where it's just sitting up against the wall, 2-hole strap. 1-hole strap, same thing. You're not going to want to use 1-hole straps for like rigid. These are pretty handy. They got a little bump on here on the inside that I think you will use these as well in the lab. I don't remember how I had it set up, but these will grab onto a 1/2 inch conduit, and boop, and you run a screw through there. Minis, malleable straps. I don't have any of those with me, but you won't be quizzed on those.
What are the corn clamps that it said on there?
I don't have any of those with me either, but I'm going to show you a picture.
Okay. I've never heard of those.
Yep, and that's all. I guess I got some other fittings I can show you. So what kind of conduit would this be for?
Rigid?
Rigid. RMC or GRC. And it's just threaded. This right here is called a close nipple. So they have different kinds of nipples. And I know you're all giggling because the name of it is nipple, but that's actually what they're called. So this is a close nipple because there's no middle part, but they make, like 3-inch nipples. Just smaller chunks of pipe that you can use to connect things. These are reducing washers. So let's say I have a panel that's already got a hole knocked out of it that's a 3/4 inch hole, or a hole for 3/4 inch pipe. This is a reducer. So I would put this over the 3/4 inch pipe, or a 3/4 inch hole, and it will reduce it down to a 1/2 inch size. So I put this one on either side of the hole, and then put a 1/2 inch connector in there, and now I have a place to run my 1/2 inch pipe out of. So those are reducing washers. This is the compression fitting that I was showing you. So if you take this apart, there's this little ring that you can see it's got a little squeezable deal there. So when you put this over the pipe, and then tighten that down, it grabs onto the conduit on the inside there. You can tighten both sides down. The other type, which is definitely, for obvious reasons, easier to use, is a set screw type coupling. You know why it's called set screw type?
Because there's a screw in it.
Because there's set screws in it. So if I'm running this into a panel and I've cut and thread this thing and it's sitting there in the panel, I pretend my fingers are the panel, and I'm pulling wire into it, sometimes this metal edge can skin up the insulation a little bit, so they make what's called bushings. This is a bushing. I don't remember what the code is, but up above a certain size rigid conduit, you are required by code to put these on inside the panel. And all it is to help that soft plastic edge when you're pulling wire, and it keeps it from skinning up the wire. That's a bushing. The only other type that I'd show you, this is called a grounding bushing. So if I'm running rigid conduit, let's say out of a whatever type of box, but let's say it's PVC. If I'm running rigid conduit out of a PVC junction box, there's no way that I have electrical continuity between that PVC box and that metal pipe, right? But I have to ground it, because what happens if one of those conductors gets energized inside this rigid pipe? It's going to also energize the conduit. This is a way to ground conduit. So you put this on the end inside the panel and then run a ground wire through here, and it grounds or bonds all of the rigid pipe to earth. Do you guys know the difference between grounding and bonding?
Yep.
Explain it.
Okay. So grounding is when you take a wire directly to an earth ground, or would go back to the source of power. Bonding is when you actually physically connect electrically all the chassis or metal parts inside something together.
Right. So if I've got a grounding electrode conductor, which is, let's say, a solid number 6 wire connected to a ground rod that's driven into the earth, and I run it through here, I have grounded this, right? And let's say I have done the same thing with another one over here. Pretend this is the same setup. Are both of them with a different ground rod? Are both of them grounded?
Yes.
Yes. Are they bonded?
No.
No, because they're not electrically continuous together. So if this was grounded and this was ungrounded, and I connected them somehow, some way, like let's say I ran a wire from here to another lug that was on this one, then I'm bonding them, because I'm making them electrically continuous.
Right.
Okay, so that's the difference between grounding and bonding. You could have 2 separate grounded systems that are not bonded. If I join them together with a wire and make them electrically continuous between the two, then I've just bonded them. That's the difference. So you'll see grounding and bonding in your code homework. This is called a lock nut. I guess I should have explained that. I'll just show you real quick. Because I'll use this type of junction box example when I start showing you different kinds of pipe bends. Here's a 1/2-inch hole. So I just ran a 1/2-inch pipe, 1/2-inch EMT, like you guys will do in the lab, to this. Okay, so the threaded, this is a 1/2-inch connector, compression fitting. So I got a pipe in here. In order to finish this off, this lock nut goes on the end. do this with my left hand. Shouldn't.
You've been out of the field too long.
I'm
sorry.
All right, the threads are all jacked up on this, but the lock nut would then go on there, and then your fiber bushing. Boop, like that. That's the setup. That's the hot setup. All right. Enough of that crap. So I showed you, this is unistrut, strut strap, spring nuts, 1-hole strap, 2-hole strap, mini or conduit hanger, but we call them minis. U-bolts. Anybody know why they call them U-bolts?
Because they're made for me.
Because they're in the shape of a U.
Oh.
This is a corn clamp. It's hard to, without having them with me, to show you how it works, but this, if you were to loosen these nuts up and bring this bracket further up, you'd have space to run conduit through the U-bolt. Then as you tighten it up, this would be like a purling that you would grab onto. So this V section grabs onto the pipe, and this flat section grabs onto the purling. I'll see if I can find an example of one that's actually hanging. Yeah, there's one. Can you see that? So behind there, this blue thing is like an I-beam.
Okay.
And then the conduit is run right underneath there. So the V part is grabbing onto the pipe. And then that flat part, which is behind here that you can't see it, is grabbing onto the beam. You tighten it up. And it's just a way to run pipe right up against an I-beam or purling or something.
Okay. So I have seen those before. I just didn't know that's what they were called.
That's a corn clamp. Here's another view of one from the side. Anyway.
All right.
Now we get into support spacing. Here we have, out of the EMT, electrical metallic tubing portion of the code. So the code will run into different requirements for each type of raceway. So section 348 obviously covers EMT. And if you notice on your Blackboard homework, oh, there's one of the answers. Look at that. NEC Article 348. So all these 340s are going to be, everything in this area here is going to be different types of code for different types of conduit. But if you have EMT, your supports. So let's say these are 1-hole straps, these red deals here. You have to be within 3 feet of a raceway termination. So either a junction box like here, or this is called an LB condulet. You need to be within 3 feet of a raceway termination, and you cannot go more than 10 feet between supports. So that's for EMT. It doesn't include, like it says, a coupling. You're not including that as a raceway termination. So here's an example here that we can go through later, but this is one of the tables that you're going to be allowed to use on your quiz. So if we were to run through an example of PVC, we okay, so I have, let's do an example here. Actually, I got to take a leak. Anybody else got to go to the bathroom? You want to take a little break?
Sure.
Nick, you just want to go to bed, don't you?
It doesn't matter to me. I stay up all the time.
Yeah, right. We'll probably go till about 11 o'clock, so I can hold it. Let's just keep going.
You sure?
Yeah, because Nick's crying about it.
Okay.
Let's see how I do this. Let's do an example here. Where'd my thing go? Can't draw without a thing. All right, so let's say that we have a pipe run that's looks like this. Junction box, and we're going into this junction box. Let's say this is 40 feet. Let's say this is 25 feet, 50 feet, and this is 10 feet. So how many total feet are in this pipe run?
125.
40, 65, 115, 125. Are we within the 360-degree rule?
90, 90. Yeah.
90, 180, 270. So we're good there. Let's say this is 2-inch PVC. What is the minimum amount of supports we can have in this system? So what do? We look at our NEC support requirements. So if we're in the code book, we're going to find that in table 352.30. Minimum 3 foot from the box. So I know I have to be 3 foot here, and I have to be within 3 foot there.
Is this in the uglies? Will that table be in there? You know?
It's a good question. I would imagine it is. Let's look after we go over this.
Okay, go ahead.
Remind me.
All right.
So if you're in the code book, though, we're running 2-inch PVC conduit. We need to be within 3 foot of a box. And maximum distance between supports, we need to look at this table 352.30. So I'm going to give you this page for your quiz. I'm going to give you this page for your quiz. This is rigid RMC. That's not PVC. The next one is PVC, rigid non-metallic conduit. So this is 352.30. So for PVC size 2-inch, we must be within 5 feet of each other on the spacing. So that's going to be a lot of spacers. That's okay. But here's how I solve these, and I recommend you do the same. So and scratch paper, here's how I'm doing if I'm quizzed on it. I got this, and then I've got, I got all this here. So this is going to be 3. I need one at, where's my next one got to be?
Well, every 5 feet, right? So got to be at 8.
8, 13, 28. Nope. 18, 23, 28, 33, 38, 43, 48, 53, 58, 63, 68. It's a bad example because there's a ton of them, but 73, 78, 83, 88, 93, 98, 103, 108, 113, 118, 123. We good? And then our box is at 125. So are we good here?
No.
Yes,
Yep.
we are, because we're within 3 feet.
Oh, I'm sorry. Yes. Yes.
So this is a long way to do it, but I recommend you do it like this every time. Because if you're off by one, if you're off by, damn it. If you're off by one spacer, you're going to get, or support, you're going to be wrong. But you will see an example. I'll try to think of a way to show you that where, but if this ended up, let's say this last spacer ended up at 121, you would know that you need to add another support, right? Because you're not within 3 feet of the box. So then all you do is just go and count them up. So 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22,
27.
24, 25. 25 supports at minimum. Make sense?
Yep.
Let's do another one with EMT.
Okay.
Okay. We'll just make this a straight shot. Let's say this is 97 feet. And let's say it's half-inch EMT. So what are we allowed minimum between here and the box? That's the first thing we got to know. So we look at this table and we've got EMT. No matter what size it is, we can be 3 foot from the box and 10 feet minimum. So that means that if it's half-inch EMT, 3/4 inch EMT, 1.5 inch EMT, it's all the same. 3 feet, 10 feet. Okay. So at 97 feet, I'm going to do my example here. Where's the first one got to be?
3.
3. We're allowed to be up to 3 feet away. Then the next one's going to be how far?
13.
10 feet, 13.
So every 10 feet. 23, 33,
Suppose you have about 11,
43.
10, I
I think
mean.
it's 11.
I'm
Not
thinking
about 10.
Oh, you did it? 53, 63, 73, 83, 93.
It'll be about 10.
Our box is at 97, right?
Yeah.
So we're good?
No, you need
No,
one
we're
more.
not, because we're not within 3 feet of this box. Very good, Justin. So we need to add one here. And it doesn't matter where it's at as long as it's within 3 feet. So let's just call it 94. Now, if this is me in real life, if I've just run and I've got one, if I've got my conduit coming up here to the junction box,
Yeah, it was 11.
and I'm 4 feet away, and I know I have to add one in there, just for aesthetics, I'm going to put it right in half. You know, to have one of these like right next to each other just looks kind of stupid. I wouldn't do that. I would put it right here at 2 feet. But either way, you know you need to add one here, right? So then you count these up: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 is right. Some people forget that last one because they got to 94 and they're not 10 feet from the box, but you still have to add one because you're not within 3. Makes sense?
Yeah.
You comfortable with those? So if we did an example with RMC, you'd be able to do it.
Yeah, I give them both tables. Yeah.
So 3-inch rigid, you'd be able to do that same example.
Yep.
3 feet of the box, and then you have to look at table 344.30B2. Well, look at that. It's right there. I'm going to give that to you. 3-inch and larger, I can be 20 foot apart. Kind of crazy, right? Why would that be?
That's what I don't understand. It's supposed to be more rigid and it's supposed to allow for stability, and the hangers are heavier, but I would think with the added weight, you would want them a little bit closer together.
You would think so, but I guess I'm not an engineer, but the fact that it's 3-inch rigid, it's kind of there's not going to be any whoopties in the pipe.
Yeah, well, but
Yeah.
I know the fasteners are way heavier for 3-inch.
Oh, I love it. It's your day, Nick. It's your day.
I appreciate it.
That's got to go in a bathroom stall somewhere.
Yeah, for sure. With Nick's phone number on it.
Oh no, not again.
Not again. Okay, so that's Conduit Sports.
In case anyone was wondering, it's page 70 in the Uglies book.
Oh, thank you.
You're welcome.
What year, what version do you have? 2017?
2017, yeah.
Page what?
70.
There it is.
There you go.
Wow, who would have known? 1 foot equals 0.3048 meters. All right, thank you.
Thanks, Brenna. So you can use your Uglies book on your quiz and your final, but I also will give you a PDF of just these 3 pages for you to use.
Okay.
Yep. It's going to look like this. Bloop. Oh,
All right.
look, also has Trig on there and take up. We haven't talked about it yet. Oh, good grief. All sorts of stuff on there. Hey, these aren't the people in my class. All right, where are we? Different methods of bending. Hand benders, hickeys. Anybody know what a hickey is?
Yep.
It's when somebody sucks on your neck and leaves a mark. Oh, I love myself. What am I doing? Oh, hickeys, hydraulic benders, mechanical benders. So what we will cover in this class, you're going to see extensively hand benders. This is a hand bender. You need to be familiar with these marks for your quiz. The arrow. And as you practice these bends, you're going to understand that, okay, for the start of a bend, I need to use the arrow. Like it'll just become kind of almost muscle memory, used for lots of different kinds of bends. The rim notch, that's used for the center of a 3-point saddle. And I should add on there, that's with 45s and 22.5s, I believe. I got to double check that. I'm gonna put it on there anyway because I think I'm right. Star, that's the center of a 90-degree, the back of a 90-degree bend. What's the degree alt code? Anybody know? 1, 2, 3. Nope. 2, 4. Nope. 2, 3, 4. Nope. I don't know. 90 ohm. That's the back of a 90 omega bend.
Nice.
The angle markings, pretty self-explanatory. If I start a bend here, see if I can do this. Nope. Okay. But if you can imagine, if I have a pipe running through here at the angle of this, and I bend it down, never mind. That's so self-explanatory, I don't even need to say it. Okay, and then note very carefully down here, most benders are going to have take-up distance for 90-degree bend. And I'll explain what that means later when I show you how to do a 90-degree bend. No, I'll explain it now. I'll explain it now because I want to. 90-degree bend. Boop. Going up into a box. A really, really small box. Why am I not using my fancy pen? Whoops, crap, that's why. I need to know, because I'm going to mark this pipe when it's flat, where this distance is, right? Because up here, there's a hole in this box that I need to hit. I'm running a pipe along here. There's my coupling that I got to get into. I need to put this last piece of pipe in here. I need to mark this pipe and bend it up so that it hits this hole, right? So how do I know where to put this mark? Well, for a 1/2-inch bender, which is what this is, I think. Actually, it says 6 inches, so that's a 3/4 inch bender. So using this as an example, 3/4 inch take up is 6 inches. That means that when I bend this pipe, the 90 itself is going to take up 6 inches worth of space. Make sense? So if I know this measurement from here to here, I guess it would be the center of this coupling. So here to here, let's say this is 18 inches. And I have a flat piece of pipe here that I'm going to bend up and hit this hole. Where do I make my mark from this point?
At 12 inches.
12. Very good. So from the end of the pipe, I'm going to make a mark at 12 inches. Bend it up. Take up is 6 inches, so this should end up right where that hole is. That's why you need take up. And just so you know, since you're going to have this on your cheat sheet, where is it at? Somewhere on here. Take up. This chart right here, you will also have on your cheat sheet. So I just said 3/4 inch take up is 6 inches, 1/2 inch is 5, 1 inch is 8. All that means is it takes up more space because you need a bigger radius bend. Could you ever bend a 3/4 inch 90 with a 1/2 inch bender?
Yeah, no, it shouldn't fit in there.
You shouldn't. Or even if you're using a 1/2 inch bender or a 1/2 inch pipe on a 3/4 inch bender, you still don't want to do that. because it's not designed for it. It's going to kink a little bit, put a little wrinkle in your pipe, that kind of thing. So make sure you use the right kind of bender for the right size pipe.
Is the take up different for 45?
Yeah, but technically there is no take up for a 45, right? Because it doesn't make a stop. So this 45 could end up anywhere. Could end up here, 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 you know. There is no technically take up for a 45.
Okay.
All right, we'll get to a good stopping point here. Run through the rest of these kind of methods of bending. This is called a hickey. It's not, when we're bending pipe, it's not the red mark somebody left on your neck. It's this thing. It's used to make small, what's called concentric bends. This picture over here is segmented bends, which involves a lot of math. We're not even going to get into it in this class. This is for like elite expert pipe benders. But if this is big rigid PVC and you're using like a hydraulic bender, you could figure out the spacing between all these marks to hit this in a 90 and do it the same for each pipe so that the spacing between the pipes is the same. You could use a hickey, you could use a hydraulic bender with a protractor. This is segmented bends, but you will see hickeys on the job site just to put little tweaks in pipe and also to use segmented bends. A hydraulic bender, this is one type. This is another type. This is called a table bender. And usually these are used for bigger diameter EMT pipe or IMC aluminum pipe. They need these big gigantic shoes with big radius on the shoe. This part right here is called a shoe, where the pipe actually bends around. We need these big diameter radius on a bigger EMT or bigger aluminum pipe so that it doesn't kink the pipe. So this is called a table bender. We don't have one of these in the lab. I'd love to get one of these, but we don't have one. They're pretty expensive just to use one time. That's why I use Chicago benders for the big pipe. But it's these are really nice to use. You see them a lot in the field. But this is called a hydraulic bender or a triple nickel. This is a Greenlee model 555. That's why they call it a triple nickel. I used to think it was called triple nipple, but I was wrong. Pretty self-explanatory though. Up here, wrapped up in this cord, is a button. And when you press the button one way, it starts to bend. When you press it the other way, it backs off. And then up here are the angle markings. And you can see this shoe has, it looks like 4 different sizes of conduit you could bend with this one shoe. So that's another type of hydraulic bender. This is the one you will see in this class. I'll do a demo of this one. It's called a Chicago bender. It's a mechanical type, and basically what it uses is leverage and muscle, your muscle. So this one can bend, it looks like 2 different sizes of pipe on the shoe, maybe 3, I think 2. And then this little hole right there, what you'll see is a pipe sticking out the end of it that when you push the pipe down, it starts ratcheting and bends the pipe up. You'll see what I mean when we do an example, but this is a Chicago bender. And this is how I bend other pipe in the lab. This is how Nick's probably going to do it too. He's going to fall asleep while he's bending his pipe.
Wait the whole time.
And here's a reamer I showed you earlier. They also make them to go in like a drill, but that's for pansies. But I have one. All right, let's call it a day there. We'll get into the types of bends on Friday. Remember, your trig homework is due Friday. Monday, we'll do a quiz on the trig homework, and we'll hopefully finish out the bend types. I'll do some examples. and get you into the lab hopefully middle of next week.
Okay.
10-4.
Hey,
Right.
Zach.
Where did everybody go?
Roger, Roger.
Hey, Zach.
What?
Could you and I go over one more of those trig problems,
Yeah.
please?
After class?
Yes.
Yep.
Thank you.
No problem. Can I take a leak first?
No.
I had to wait because Nick's been crying about it the whole time.
I'm the one paying tuition. I call the shots.
Oh damn.
I kind of would like to go over some more too.
Yeah, go do your thing. I'll be here.
When you get a chance, Zach, can I talk to you supervisorly for my classes and stuff? Just whenever.
Yep.
All right. Thank you, sir.
Hey, what I'm going to do, I'm going to go take a leak, and I'm going to come back, and whoever wants to talk to me about whatever they want to can.
Okay.
Thank you too.
See you, Zach.
See you guys.
See ya.
See ya.
I'm going to stop the recording then.
Okay.